Thank you, Dr. Evans, for the introduction. The title of my work is TinyGarble. It's a tool for highly compressed and sequential garbled circuit. The main idea behind this tool is to use the knowledge that we have in hardware synthesis and hardware design to make Yahoo's garbled circuit more and more practical. Okay, let's look at the motivation behind this work. We want to solve the problem of secure function evaluation, or SFE. In SFE, the goal is to compute a function jointly between two parties on their private data. An example is Yahoo's millionaires problem, where two millionaires want to compare their wealth without letting each other to know what was their amount of money they have in their bank account. There are a couple of solutions. One of them is Yahoo's garbled circuit solution, which seems to be the most promising one. We are focusing on two-party GC protocol, or Yahoo's garbled circuit protocol. Let's see how it works on the same problem of Yahoo's millionaires problem. The first step is to make a Boolean circuit out of function f. Here is comparison, so we need a 3-bit comparison here in this example, which is this circuit. The next step, Alice needs to make a garbled circuit, which is the randomized and encryption circuit, the same as the Boolean circuit. Alice also encrypts all the truth table in this randomized circuit and sends them to Bob. Bob cannot open them unless he has the input labels or input randomized wires. Alice sends her inputs to Bob, and through a protocol called oblivious transfer, or OT, Bob receives his input. So Bob has all the input wires, so we can go ahead and open each of these encrypted truth table to get the final output. After this, he can share it with Alice to find out what was the actual output. So the question is, can this protocol be practical? Can we actually implement it and use it? Thanks to lots of people works in this field, it is practical. It has been practical since 2004, for a decade. And this is the chronology of the work on the implementation of garbled circuit. And we saw that many of this work try to implement a compiler or a library to solve the problem in the first step of garbled circuit, which is making a Boolean circuit out of a function description. And still, there are some shortcomings in this step. Poor scalability. Many of this work has a poor scalability and prevents user from making a large circuit. And some of them ask user to manually optimize their circuit, so they don't provide any automatic tools for them. Also, some of them use online circuit generation, which doesn't provide any global optimization for the function because we don't have the circuit at the time, so we cannot optimize it. Also, it's waste of time of garbling. And some of them also provide high-level abstraction, which usually result in inefficient optimization compared to manual optimization. Okay, what's our approach? We thought maybe we can use hardware synthesis tools and techniques that have been around for half a century, and they are used for the same purpose, translating a function description into a Boolean circuit, but for different objective, for actual hardware and actual device. So we want to hack these tools to make them able to generate an optimized circuit for GC protocol instead of actual hardware. The next one is a concept in hardware design, a sequential circuit, which makes us enable to make scalable circuits for the complex functionality. Okay, let's look at our detailed contribution. The first one is the adaptation of these HTL synthesis tools for generating an optimized garbled circuit. So we have an offline circuit generation. We don't do it online. Also, it's automatic. User doesn't need to do anything. Also, we create some new custom libraries and objective to change the purpose of these tools, to hack them, to get an optimized circuit for GC protocol instead of optimized circuit for actual hardware. Also, we introduced sequential circuit description for GC. It makes us enable to have a compact circuit representation and limited memory footprint during garbling and evaluation. Also makes us enable to use the knowledge that we have in hardware design for making function in garbled circuit. For example, we provide a scalable solution for private function SFE or PFSFE. Okay, based on these ideas, we generated a tool called TinyGarble. Let's see how it works. This is the global flow of TinyGarble. A user can start from a high-level description of a function like C or C++. Our tools translate it to a hardware description language or HDL, Verilog or VHDL. Or alternatively, user can start from Verilog or VHDL. Most of the hardware design are done in these languages. Then the next step is hardware logic synthesis tools with our objective and constraint, which is hacked for generating optimized garbled circuit. It results in a netlist. Netlist is essentially the answer. It has all the gates and its connection. So we want this netlist be optimized for garbled circuit. The next step is the scheduling, which is a topological sort. Then we store it in a portable format so we can distribute it and use it during garbling and evaluation. So what about the sequential circuit? What is sequential circuit? Usually when we are thinking about a Boolean circuit in garbled circuit, we are referring to a type of circuit called combinational circuit in hardware design. In combinational circuit, outputs are only function of inputs. So we have a directed cyclic graph from inputs to the output. There is no loop. While in sequential circuit, outputs are function of inputs and also state of the circuit, which are kept in some memory elements, like flip-flops. So we have a loop here. It's not DAG anymore. All the hardware design are done in sequential circuit, not the combinational circuit. Because if we want to design a computer wholly on a combinational circuit, for a simple task, a computer would be the size of this room. It's not scalable. And also, it's not just unrolling the loop or having this memory for the loop. It can do many exciting stuff that we cannot think about it with the loops only. For example, shift register or a counter. If we mix them together, we cannot think about them as a loop. They're just a memory element for reusing them later in the circuit. OK, let's look at an example and see how it works. This is an n-bit adder for combinational circuit. We have n-1 full adders and 1 half adder. Full adder has a carry in, carry out. Half adder doesn't have a carry in. So the size of this circuit is O(n). While in sequential circuit, we can have only 1 full adder and reuse the carry in as carry out as a carry in for the next cycle. So we need to repeat this circuit n times or n sequential times to have the same functionality as a combinational circuit. Number of gates here is O(1). We only have 1 full adder. No matter how arbitrarily large n is, the circuit is this. So it's very compact. It's scalable. Also, it's very easier to optimize. If we want to optimize this, the sequential circuit is much, much easier. But there is no free lunch, unfortunately. There is a small overhead here. If you remember, half adder was a little bit simpler than full adder. In sequential circuit, we need to repeat a full adder n times. So it means we are doing a full adder minus a half adder more compared to the combinational circuit. This is because of the asymmetry in the loops of addition, which in the first iteration, we have a half adder. The rest is full adder. If you notice, I ignore the flip-flop because we don't need to actually implement the flip-flop in an abstract level in the garbled circuit. Flip-flop is just transferring a label from one wire to another wire in garbled circuit, so it doesn't have any overhead. Sequential circuit makes us able to solve many exciting problems. For example, private function SFE. where a user has a function, the other user has a data, and they want to jointly compute f of x. The current solution is to reduce this problem to a SFE, to a normal SFE, using a universal circuit, a circuit that gets the circuit as an input and a data and evaluate that circuit. Unfortunately, it's not scalable. The size of this circuit increases with the size of the function f. So we are looking for a scalable alternative for the universal circuit. What about processor? They are implementation of universal Turing machine. They receive a function f as a binary code in their memory. They receive an x as initial data in their memory, and they write something as an output in their memory. And the size of the processor is independent of size of f, is O of 1. If we have a laptop with a limited area, and we can do whatever we want with it. Doesn't matter what is the function. And the time complex is very straightforward, is O of m, which m is number of instruction in the function that we have. And the question is how to securely evaluate it with the garbled circuit. The good news is that processors are sequential circuit. If we can support sequential circuit for garbled circuit, we can use these processors into the garbled circuit. And they have, you can go ahead and on internet and download them. They have available compiler. So it's very straightforward to implement them if we can support sequential circuit. OK, let's look at the evaluation. At the first step, we want to see the effect of hardware synthesis tools. So we just compare our combinational circuit with previous work. So we don't have any sequential circuit. The next step is comparing sequential circuit with what we generate and also the previous work. We use two metrics. The first one is memory footprint efficiency, which is comparison between total number of gates in two circuits. Why we call it memory footprint? Because for every gate in a circuit, we have to store a label during garbling and evaluation in the memory. So if we can reduce number of gates in a circuit, we are reducing memory footprint of garbling and evaluation. Higher MFE is better, meaning that the circuit and the size of circuit is reduced compared to the reference circuit. The next one is number of garbled table that is generated during garbling, which is number of non-XOR times C, which C is number of sequential cycle. For combinational circuit, C is 1. Why number of non-XOR? This is due to optimization called free XOR that led us to garble only non-XOR gate, and XORs are free under this optimization. And it's a very, very good estimation of the cost of garbling and evaluation. So we look at the GT difference in a percentage to see if the circuit is more optimized or less optimized. Negative GTD means the circuit has a less number of non-XORs. We compare our combinational circuit with PCF. PCF at the time of writing was the best automatic tools for generating garbled circuit. So let's look at GTD compared to PCF and also MFE. For example, for multiplication 64-bit, we have 9.3 times a smaller circuit compared to what PCF can generate. And also at the same time, it's 84% more optimized, meaning the cost of garbling is reduced by 84% just by using hardware synthesis tools and hack them to optimize the circuit for garbled circuit. OK, let's look at sequential circuit. We compare them with our combinational circuit and also PCF. Again, multiplication 64. We can reduce the size of circuit by 20 times compared to our combinational circuit by sequential circuit, and 200 times compared to what PCF can do. So it's much more compact. GTD, number of non-XOR compared to PCF, is negative 80%. So the number of non-XOR is reduced by 80%. But when we are looking at GTD compared to our combinational logic, we see a positive number, 28% more number of non-XOR. This is due to the overhead of sequential circuit, because multiplication 64-bit doesn't have a symmetric loop. So here's the deal. We can use a combinational circuit and have a very optimized circuit, but it's not scalable. We cannot do it, for example, for multiplication 1024. It's not practical. We have to make a sequential circuit to be able to optimize it using these tools, because they are designed to optimize small circuits for the actual hardware. They are not designed to do combinational circuit for such a huge circuit. But still, you can see the GTD, the comparison between non-XOR is still better than previous work, because these tools are designed for making optimized circuit. Okay, in conclusion, we look at GC Boolean circuit generation as an atypical logic synthesis task, where we change the objective of hardware synthesis tools for generating an optimized circuit for garbled circuit, meaning reducing number of non-XOR in these circuits. We also introduced sequential circuit description, which beside reducing the size of circuit, it makes us enable to do many exciting circuits that are available in hardware design. For example, k-nearest neighbor using sequential circuit is pretty easy to think of, while with combinational circuit, it's very hard to design. Also, a scalable private function SFE using a processor circuit, which the circuit size is independent of the number of instructions that we have. So you can see using those knowledge that we had in the hardware design and hardware synthesis makes us enable to do many exciting things for garbled circuit. Thank you. Any question?
Hi, thanks for the talk. So you surely, and it said on the slide, you have to have a separate garbling table and separate wire labels for each time around through the thing. You said
we actually replace the garble table and the wire labels each time on the same circuit. So we don't need to store them in a memory. We just replace them because we don't need them.
Okay, so you are still generating.
Yeah, still the time and everything is same.
Okay.
With sequential circuit.
You're just throwing, you can
Yeah,
throw
we're
the
just
old one
repeating
away.
the circuit and send the garble table, for example, to the other user. But the thing is, the memory footprint is much smaller because we know how much wire we have in this circuit.
Right, so some previous work also could figure out that, okay, I'm never going to use these wires again and dump it out of memory.
Yeah, but the thing is, here it's very simpler. We exactly know before starting the garbling or evaluation, we know exactly how much memory we have to allocate for this circuit, because we have the circuit at a time.
Thank you.
So I ask one question. So to someone who doesn't work with these hardware synthesis tools, it seems like there are these magic, super powerful tools people have been working on for 40 years.
Yeah.
That you put a circuit, put logic description in and get circuits out. So the question is, can you found this trade-off between the garbling cost and the memory footprint. Could that be part of the input to the synthesis tools if you didn't want to, you wanted to generate a circuit that doesn't increase the garbling cost?
We sweep the number of folding the circuit or the number of sequential circuit we need to evaluate a sequential circuit. We sweep it from 1 to the maximum, and we find out which one is better. Actually, the number of, the size of the circuit will reduce definitely, and also the number of non-XOR will be increased because of the asymmetry. If it doesn't have a asymmetric in its loop, it will be static. So it actually depends on the function. We cannot ask those tools to do it for us. We need to do it manually.
Thank you.